The Tomahawk cruise missile doesn't look particularly impressive sitting on its launcher. It's 18 feet long, weighs 3,500 pounds, and resembles an oversized model airplane more than a weapon of war. There's no dramatic rocket plume at launch, no supersonic shockwave, just a turbofan engine that sounds like a small jet, propelling the missile at a relatively pedestrian 550 miles per hour. But that unremarkable appearance hides one of the most lethal and precise weapons ever created. A missile that can fly 1,000 miles, navigate through enemy air defenses at treetop level, turn corners around buildings, and strike a target the size of a window with near-perfect accuracy. A weapon so versatile it can be launched from surface ships, submarines, and ground-based platforms. And a system that has fundamentally changed how modern nations project military power across vast distances. This is the story of the Tomahawk cruise missile, how it was developed during the Cold War to strike Soviet targets from standoff range, how it evolved through 5 generations of technology to become the most capable land attack missile in the world, why Ukraine is desperately requesting it for strikes deep into Russian territory, and why this 40-year-old weapon remains more relevant today than when it was first designed. If you're here for weapons technology analysis and the strategic implications of long-range precision strike, hit subscribe on AirPower right now, and comment below, should the United States provide Tomahawk missiles to Ukraine? The Tomahawk's development began in the 1970s during a period when the United States faced a critical problem: how to strike Soviet targets without exposing aircraft and pilots to the USSR's formidable integrated air defense system. Soviet SA-2, SA-3, and SA-5 surface-to-air missiles had proven devastatingly effective against American aircraft in Vietnam and the Middle East, and the Soviet homeland was protected by thousands of these systems, along with radar networks and interceptor aircraft that made deep penetration strikes suicidally dangerous. The solution was a cruise missile, an unmanned aircraft that could fly low enough to avoid radar detection, slow enough to use terrain-following navigation, and cheap enough to be expendable. If a $1 million missile could accomplish what a $30 million aircraft and trained pilot risked doing, the strategic calculus changed dramatically. Development was contracted to General Dynamics in 1972, with the goal of creating a missile that could be launched from ships and submarines, fly up to 1,500 miles, navigate autonomously using terrain-matching guidance, and deliver either conventional or nuclear warheads with precision measured in feet, not miles. The first operational Tomahawk missiles were deployed in 1983 aboard U.S. Navy ships and submarines. The early variants used a combination of inertial navigation and a terrain matching system called TERCOM that compared radar images of the ground below with pre-programmed maps stored in the missile's computer. The modern Tomahawk Block V missile represents 4 decades of continuous improvement, but the basic design philosophy remains unchanged: subsonic speed, low-altitude flight, and extreme precision through sophisticated guidance systems. The missile measures 18 feet 3 inches in length with a diameter of 20.4 inches. Its wingspan when deployed is 8 feet 9 inches. Total weight is 3,500 pounds, with a 1,000-pound high-explosive warhead. Maximum speed is 550 miles per hour, Mach 0.74, which seems slow compared to supersonic weapons, but provides critical advantages in fuel efficiency and radar detectability. Range varies by variant. Block 4 missiles can fly 1,000 miles, while the newest Block V extends that to over 1,200 miles. During terrain-following flight, the Tomahawk cruises at altitudes between 50 and 150 feet above the ground, and accuracy is measured within 10 feet of the target, precision that would have been considered impossible when the program began. The Tomahawk uses a Williams F415 turbofan engine producing 600 pounds of thrust. At launch, a solid-fuel rocket booster accelerates the missile away from the launch platform, burning for just 2 to 3 seconds before dropping away. The turbofan engine then starts, air intakes deploy from the body, and wings unfold from their stowed position. The missile begins its cruise phase, flying at subsonic speed for maximum fuel efficiency. The turbofan design gives the Tomahawk exceptional range compared to rocket-powered missiles. While a rocket burns all its fuel in minutes, the turbofan sips fuel for hours, allowing the missile to cover distances that would be impossible for faster weapons. Subscribe to Air Power for Weapons Technology Deep Dives that explain how modern precision strike systems actually work. And tell us, is range more important than speed in modern missiles? Modern Tomahawk missiles use multiple overlapping guidance systems to ensure accuracy even when individual systems are jammed or degraded. The inertial navigation system uses ring laser gyroscopes and accelerometers to track the missile's position from the moment of launch. While INS alone would accumulate errors over long distances, it provides the baseline navigation data that other systems refine. GPS navigation receives signals from GPS satellites to correct INS drift and maintain accurate positioning. The military GPS signal is encrypted and jam-resistant, providing meter-level accuracy throughout the flight. Terrain contour matching, known as TERCOM, is what makes the Tomahawk truly special. During flight, a radar altimeter continuously measures the height of terrain below the missile. This data is compared in real time to preloaded digital elevation maps stored in the missile's computer. By matching the actual terrain profile to the stored map, the missile can determine its exact position even without GPS. This makes the Tomahawk resistant to GPS jamming and electronic warfare, capabilities that are increasingly important as adversaries develop sophisticated denial systems. In the terminal phase, digital scene matching area correlation activates. An optical camera captures images of the target area and compares them to reference images stored in memory. This allows the missile to identify specific buildings or even specific windows, achieving precision measured in feet rather than meters. The combination of these four guidance systems, INS, GPS, TERCOM, and DSMAC, ensures that the Tomahawk can navigate accurately through any environment and hit targets with exceptional precision. A typical Tomahawk mission follows a carefully choreographed sequence. Launch occurs from either a Mk-41 vertical launch system on surface ships or from torpedo tubes on submarines. The solid rocket booster fires, accelerating the missile away from the platform in 2 to 3 seconds before separating. The turbofan engine starts, wings deploy, and the missile begins its cruise flight at low altitude. Throughout the mid-course phase, the missile flies 150 feet above terrain, using TERCOM to navigate around obstacles and maintain its flight path. Modern Block V missiles can receive mid-course updates via satellite data link, allowing operators to retarget the weapon even after launch. In the terminal phase, DSMAC activates. The missile identifies the precise target using stored imagery and guides itself to impact. The 1,000-pound warhead detonates on contact, delivering devastating explosive force to the target. What makes the Tomahawk stand out among cruise missiles isn't any single characteristic. It's the combination of capabilities that no other weapon system matches. First, extreme range with precision. Most precision-guided weapons have ranges measured in tens of miles. A laser-guided bomb must be dropped from an aircraft directly over or near the target. A GPS-guided JDAM has a glide range of perhaps 15 miles. But a Tomahawk can strike targets 1,000 miles away with the same precision as weapons delivered from directly overhead. This standoff capability is strategically decisive. A ship or submarine 1,000 miles from a target is virtually invulnerable to retaliation, while the target faces destruction from a weapon it may not detect until impact. Second, terrain-following flight capability. The Tomahawk flies at altitudes between 50 and 150 feet during most of its flight. At these heights, the missile is below the radar horizon for most air defense systems. A radar 50 miles away cannot see an object flying at 100 feet altitude because the curvature of the Earth blocks line of sight. Even when the missile is detected, its low altitude makes interception extremely difficult. Most surface-to-air missiles are optimized for high-altitude targets, aircraft flying at 20,000 feet or higher. Engaging a target at 100 feet altitude, moving at 550 mph, weaving through terrain, is extraordinarily challenging. Third, GPS-independent navigation through TERCOM. Unlike many modern weapons that rely entirely on GPS, the Tomahawk can navigate accurately, even in GPS-denied environments. This makes the missile resistant to GPS jamming, which is increasingly common in modern warfare. Russia, China, and other nations have developed sophisticated GPS jamming systems, but the Tomahawk's ability to navigate using terrain matching means it remains effective even when satellite navigation is unavailable. Fourth, in-flight retargeting capability. Modern Tomahawks can receive new targeting information while in flight via satellite data link. If intelligence identifies a more valuable target, or if the original target moves or is destroyed by another weapon, the missile can be redirected to a new target. This flexibility is unique among long-range strike weapons and allows commanders to respond to rapidly changing battlefield conditions. Fifth, multi-platform launch versatility. Tomahawks can be launched from surface ships equipped with Mk-41 vertical launch systems, submarines equipped with torpedo tubes or vertical launch systems, and ground-based launchers currently in development. This versatility means nearly every major U.S. Navy surface combatant and submarine can carry and launch Tomahawks, distributing strike capability across the fleet, rather than concentrating it in a few specialized platforms. Sixth, warhead versatility for different target types. The Tomahawk can carry different warhead configurations. A unitary warhead with 1,000 pounds of high explosive for hardened targets like bunkers and command centers, submunitions that disperse over area targets, and penetrator warheads designed to punch through layers of concrete before detonating inside underground facilities. The Tomahawk's combat debut came in January 1991 during Operation Desert Storm. U.S. Navy ships and submarines launched 288 Tomahawks at Iraqi targets in the opening hours of the war. The missiles struck command and control facilities, air defense sites, communications nodes, and other strategic targets, often with dramatic precision captured on video that was broadcast worldwide. One particularly famous strike hit the Iraqi Air Force headquarters in Baghdad. The missile flew through the city at low altitude, turned a corner around a building, and entered through a specific window, exactly as programmed. The precision was unprecedented and announced to the world that standoff strike warfare had fundamentally changed. Since 1991, Tomahawks have been used in every major U.S. military operation. In Bosnia, in 1995, 13 missiles struck Bosnian Serb air defense sites. Multiple strikes against Iraqi military facilities occurred in 1996 and 1998. In 1998, 75 missiles struck al-Qaeda training camps in Afghanistan following embassy bombings in Kenya and Tanzania. Over 200 missiles struck Serbian targets during the Kosovo campaign in 1999. The opening strikes of Operation Enduring Freedom in Afghanistan in 2001 included extensive Tomahawk strikes. Over 800 missiles were launched during Operation Iraqi Freedom in 2003. In Libya in 2011, 124 missiles struck Libyan air defenses and military facilities during the international intervention. Syria was hit with 59 missiles in 2017 targeting chemical weapons facilities, and additional strikes occurred in 2018. Yemen saw Tomahawk strikes against rebel radar sites in 2016. Total combat launches exceed 2,300 missiles with a success rate estimated above 85%, meaning the vast majority hit their intended targets and detonated as designed. This combat record is unmatched by any other long-range precision weapon system. The Tomahawk has evolved through multiple generations, with two variants currently in service. Block I-4, known as the Tactical Tomahawk, was introduced in 2004 and added two-way satellite communications for in-flight retargeting, loitering capability, allowing the missile to circle a target area for hours, waiting for a target to appear. Battle damage indication, where an onboard camera can transmit post-strike imagery back to commanders, and enhanced GPS and TERCOM for improved accuracy in all conditions. Block V, the newest variant entering service in 2021, represents a fundamental capability expansion. It adds extended range with exact figures classified, but estimates suggesting 1,200 miles or more. A multi-mode seeker combining radar and imaging infrared that allows the missile to engage moving targets including ships, enhanced networking capabilities with other platforms for coordinated strikes, and improved electronic warfare resistance against increasingly sophisticated jamming systems. The Block V's ability to engage moving ships is particularly significant. Previous Tomahawks could only strike fixed, pre-planned targets, but Block V can hunt and destroy naval vessels, making it a credible anti-ship weapon in addition to its land attack role. Subscribe to Air Power for strategic weapons analysis that explains why certain systems change the balance of military power. And comment, should cruise missiles be able to engage moving targets, or should they remain specialized for fixed targets? In 2024 and 2025, Ukraine repeatedly requested Tomahawk missiles from the United States to strike Russian military targets deep inside Russia, command centers, logistics hubs, air bases, and ammunition depots located hundreds of miles from the front lines. The strategic rationale is clear. Ukraine faces a larger adversary with significant strategic depth. Russian forces can position command posts, supply depots, and air bases far from Ukrainian artillery and aircraft range, allowing them to operate with relative impunity. Tomahawks would change that calculus dramatically, putting targets 1,000 miles inside Russia at risk from Ukrainian strikes. The military benefits would be substantial. Ukrainian forces could strike Russian bomber bases launching cruise missiles at Ukrainian cities. They could destroy ammunition depots supplying Russian artillery. They could hit railway junctions critical to Russian logistics. And they could target command centers coordinating Russian military operations, potentially disrupting the entire Russian war effort. The psychological impact would be equally significant. No Russian military facility would be safe, forcing Russia to disperse forces, divert resources to air defense, and constantly worry about strikes from weapons they cannot easily intercept. However, the United States has been reluctant to provide Tomahawks for several compelling reasons. First, escalation risk. Providing weapons capable of striking deep inside Russia could be perceived as direct U.S. involvement in the conflict, potentially triggering Russian retaliation against NATO member states, or even nuclear escalation. Russia has repeatedly threatened to treat weapon supplies as acts of war, and Tomahawks represent a qualitative leap in capability that might cross Russian red lines. Second, technology security concerns. The Tomahawk contains extremely sensitive technology, guidance systems, encryption, radar systems, and propulsion technology that the United States does not want falling into Russian hands. If a missile fails and crashes intact, Russian engineers could reverse engineer critical systems, potentially compromising decades of technological advantage. Even recovering fragments could provide valuable intelligence about U.S. weapons capabilities. Third, strategic stockpile limitations. The United States has a finite number of Tomahawks in inventory, and current production rates are limited to approximately 400 missiles per year. Providing large numbers to Ukraine, estimates suggest Ukraine would need at least 200-300 missiles for a sustained campaign, would deplete U.S. inventories needed for potential conflicts with China, Iran, or North Korea. The U.S. military plans for scenarios requiring thousands of cruise missiles, and transferring hundreds to Ukraine creates risk elsewhere. Fourth, targeting intelligence requirements. Tomahawk missions require detailed intelligence that Ukraine may not possess for targets deep inside Russia. The TERCOM system needs high-resolution terrain elevation maps. The DSMAC system needs optical imagery of target buildings. Flight paths must be programmed to avoid air defense systems. Without this intelligence infrastructure, providing the missiles would be ineffective. The U.S. would need to either provide targeting data directly, making it a direct participant in strikes on Russia, or help Ukraine develop its own targeting capabilities, which takes years. Fifth, launch platform limitations. Ukraine has no ships or submarines capable of launching Tomahawks. Ground-based launchers exist, but are experimental systems still in development. The U.S. would need to provide not just missiles, but entire launch systems, train Ukrainian forces to operate them, and then protect those launchers from Russian strikes. Mobile launchers would need to constantly relocate to avoid being targeted, and static launchers would require extensive air defense protection. Despite these concerns, some analysts argue that providing a limited number of Tomahawks, perhaps 50 to 100 missiles with strict targeting restrictions, would give Ukraine disproportionate strategic leverage without unacceptable escalation risk. The ability to hold at risk even a limited set of Russian military targets far from the front would force Russia to disperse forces, divert resources to air defense around critical facilities, and complicate their logistics networks. The psychological impact of Russian military commanders, knowing that any concentration of forces or supplies 1,000 miles from Ukraine could be destroyed without warning would be substantial. As of late 2025, the United States has not approved the transfer, instead providing ATACMS missiles with a 190-mile range as a compromise solution. But the debate continues within U.S. policy circles, with some advocating for gradual escalation of capabilities provided to Ukraine. Even as the Tomahawk remains highly capable, the United States is developing next-generation weapons to complement or eventually replace it. Hypersonic weapons traveling at Mach 5 or faster can strike targets in minutes rather than hours, though they currently cost 10 to 20 times more than Tomahawks and remain in early development. Long-range anti-ship missiles like the AGM-158C LRASM combine Tomahawk-like range with advanced anti-ship capabilities and are entering service. Future concepts envision autonomous swarming munitions where dozens of coordinating missiles overwhelm defenses through sheer numbers and distributed intelligence. But for the foreseeable future, likely through the 2040s, the Tomahawk will remain the backbone of U.S. long-range strike capability. Continuous upgrades keep the system relevant, proven reliability gives commanders confidence, and unmatched precision ensures effectiveness. The U.S. Navy plans to keep Tomahawks in service for at least another 20 years, with ongoing development of Block 6 and future variants adding new capabilities as technology advances. The Tomahawk cruise missile represents 40 years of continuous evolution in precision strike warfare. What began as a Cold War weapon designed to penetrate Soviet air defenses has become the defining standoff weapon of the modern era. A system that allows military commanders to strike targets anywhere on Earth with precision, minimal risk, and strategic effect. Its combination of extreme range, terrain-following flight, GPS-independent navigation, and proven combat effectiveness makes it unique among weapon systems. And its evolution continues, with Block 5 variants adding capabilities that extend its relevance decades into the future. For nations facing powerful adversaries with strategic depth, like Ukraine confronting Russia, the Tomahawk represents a capability that could fundamentally change the strategic balance. The ability to hold at-risk targets 1,000 miles from the front lines forces adversaries to disperse, defend, and constantly worry that any concentration of forces or supplies could be destroyed without warning. Whether the United States will provide Tomahawks to Ukraine remains an open question, driven more by political and strategic calculations than by technical limitations. But the request itself demonstrates the missile's enduring reputation as the gold standard for long-range precision strike. Now I want 3 perspectives from you. First, should the United States provide Tomahawk missiles to Ukraine, or does the escalation risk outweigh the military benefits? Second, in an era of hypersonic weapons, does the subsonic Tomahawk remain relevant, or is it becoming obsolete? Third, what's more strategically valuable, a few expensive, sophisticated weapons like Tomahawks, or many cheaper, shorter-range systems? Comment your detailed strategic analysis below. Your insights drive the conversations we have on air power. And if this deep dive into the Tomahawk cruise missile gave you new understanding of why this 40-year-old weapon remains the most feared long-range strike system in the world, prove it by hitting that like button, subscribing to Air Power, and turning on notifications. Because in modern warfare, the ability to strike anywhere, anytime, with precision, changes everything. Until next time, stay informed, stay tactical, and remember, range is freedom and precision is power.